from the homework assignment from last time. So I asked you guys to work on numbers 1 through 12, and obviously nothing is due today, right? The homework check is Sunday at midnight. And you'll just put your work into OneNote in the homework tab, labeled appropriately, and that's all you need to do. There's no Dropbox, there's no picture, there's nothing like that. I'll see it directly from your OneNote. Just make sure you've synced before you say, okay, I'm done. And that should be that. But one of the points of having the homework due just once a week is it allows you to look at it, and if there's questions on things or stuff you're not sure about, or like, ooh, I don't know if I did that right, or I'm positive I didn't do that right because the odd answer doesn't match what I got. It allows you to kind of come in, we can ask some questions and get a little bit more feedback and fill in the blanks and finish, so you're able to kind of finish up and do a little bit more complete job than maybe you would normally. So I'd like to take a few minutes here at the start. If anybody has any questions from that assignment 1 through 12, and if you don't, that's perfectly fine. Did you guys check in at the office?
Yeah, we did.
Perfect, thank you. It's not a tremendously difficult assignment, but if you have questions about things, I'd be happy to talk a little bit more, address them, or work through something or whatever. Does anybody have anything they want to talk about? John?
Can we go through together number 8?
Number 8? Sure. Just grab you. Okay. So number 8, here we're asked to find the domain of the function algebraically, and then to express our answer using interval notation. Okay? So number 8 is, I don't remember, it doesn't really matter, I guess, f of x over x squared minus 1. And I guess it's probably not f of x, but it's something of x. It doesn't, whatever, it doesn't really matter. So when I look at this function, I notice that it's context free. It's not part of like a story problem or whatever, so I know the implied domain there is just going to be all real numbers. So that doesn't really do much for me. So now I'm going to look at the relevant domain. There I'm going to look at the operations kind of involved in this problem. And I see like 3 operations, right? I see squared, I see subtraction, I see division. So when I think about real numbers, if I subtract 2 real numbers, that'll always give me an answer, right? If I square a real number, that'll always give me an answer. But if I divide 2 real numbers, that's a place where I could get into some trouble, because there is one number that I can't do division with, and it's 0, right? We can't divide by 0. So what I'm going to want to do is I'm going to want to take the denominator, that's the like divisor of my division problem, and say that that cannot equal 0. So far, so good. Now, this is a quadratic equation. To solve a quadratic equation, there's a couple of different methods you could use. You could use the quadratic formula. You could factor. You could solve this directly. This is one where I think factoring is probably the easiest route, because you should recognize this as a difference of 2 squares, something that factors to x plus 1 and x minus 1. And then if we apply the 0 product property, we can take each of those factors and set them equal to 0 separately. So I have that x cannot equal -1 and x cannot equal +1. However, to write interval notation, it would be easier if I had inequalities instead of these not equal to's. So if I think about the stuff that's not equal to -1, that would be all the x's that are less than 1, or all the x's that are greater than -1. And here, similarly, I'd have all the x's that are less than 1, or all the x's that are greater than 1. But here's a little bit of a problem, is when I have two solutions like this that are not equal to, like I have here, I really have an and going on in between them. So what this is really going to say here, and this is a little bit tricky because we didn't see an example like this. If I think about the things that are less than -1 and the things that are less than, actually let's think about it this way. Let's just think about it on the number line because that'll be easy to illustrate kind of what's going on. Okay? So I have less than -1 or greater than -1. And then I have less than 1 or greater than 1. So really the parts of the number line that are going to be covered are this one, and this one. You kind of see that?
Yeah.
Okay. And again, I'm doing this a little bit differently because the problem is like I've got to a confusing part, right? Where it's like, oh, I have all of these different inequalities and like some of them are overlapping, right? Like the stuff that's greater than -1 and the stuff that's less than 1, like some of that stuff overlaps, right? And it's like, how do I, like, my intervals shouldn't be overlapping. So it's one of these where, like, if I draw a picture of what I really have, it becomes a little bit clearer what's going on here. So, like, this piece, those are the x's that are less than -1. This piece are the x's between -1 and +1. And this piece are just the x's that are greater than 1. Is that okay? And now I have gone ahead and kind of constructed this in a way that none of these inequalities are overlapping, right? The stuff that's less than -1 doesn't overlap any of the stuff in between -1 and +1, and that doesn't overlap any of the stuff that's greater than 1. So if I look at x is less than -1, the lower bound on that is -infinity, and the upper bound is -1. The infinities always get a parenthesis, and because it's a strict less than, the -1 gets a parenthesis. And I have my union symbol. The next interval, the lower bound is -1, and the upper bound is +1. Both of those inequalities are less thans, so both of those get a parenthesis. And then because I have another or, I get another union. And on the last inequality, x is greater than 1, my lower bound is 1, and my upper bound is +infinity. The infinities always get a parenthesis, and because it's a strict greater than, the 1 gets a parenthesis. So my final answer for that one would be x is a member of yada, yada, yada.
Thank you.
Yeah, you're welcome. And again, I like hyper explain that, like the amount of work and stuff that I showed is not necessary. My expectation, or not necessarily my expectation of what you guys would have done, but we asked a question about it. So I want to really kind of talk through it and make sure that we have an idea of like, okay, so I got here. This seems like the sensible way of starting it, probably the way that you would have started it. And then we get to a place where we're kind of stuck, and I'm going to explain to you kind of what it is that we're seeing here and how to like reinterpret it to a, to a form that's going to be easy to deal with. And obviously, like, I don't expect that you guys would have those same ideas on how to deal with it, but I would expect that like once you've seen like, oh, that's a, like I can just rewrite all these different inequalities on the number line and kind of look at the picture and then reform the inequalities from the picture. That I think is a fairly reasonable thing to expect once you've seen that as a, like, oh, that's a clever workaround. I could do that again. You know, because drawing an inequality on a number line is like an Algebra 1 skill, right? That's something that we should be able to do, or even pre-algebra skill. I think that's maybe even like an elementary skill, right? Where you draw an inequality on the number line. Feels like something we've done for a long time. Anyways, others. Is there anyone else that wants to talk about any of these from the homework? Again, it's not your last chance to do this. We could still come back to stuff. Claire? 6. Oh, okay. X squared minus 1. So again, there's no context given here, so I know my implied domain is just all real numbers, right? So to find my relevant domain, I'm just going to look at the operations involved in my function. I see two operations. I see squaring and I see subtracting. So if I take two real numbers and I subtract them, always going to get another real number back. There's always an answer to that. If I take a real number and square it, always going to have an answer to that also. So what does that tell me? The relevant domain is just the same as the implied domain. The actual operations in the function don't actually restrict down my implied domain any further than it was before. So it's just the same thing as the implied. And that's it. So that's not so bad. Anybody else? Lily? 2? I mean, anything is possible. Do the following represent y as a function of x? Sure. So, what was it? Is it x squared? Yeah. So what I'm going to do is I'm just going to like pick some values for x and see if I get more than one value of y. And if it seems like I'm always getting one value of y, maybe I'll think a little bit harder about it, like, is there any specific special value for x I could pick that I haven't just tried arbitrarily, and see if I get more than one value for y there. Like, think about it a little bit harder, but this one, it won't be bad. So I'm just going to say, let's pick an x that's easy to deal with, maybe 0. If I do that, I get 0 plus or minus 1. So that really tells me y equals 1 or y equals negative 1. So since that x is being connected, that x0 is being connected to two y coordinates, it's not a function, right? This is basically saying that we have the mapping diagram here, that I have something like this happening. Does that make sense? So right away we know this is no. And really any x you pick, you're going to get that behavior for this one. So there's nothing tricky about that one. There might be, I didn't look at the problem super closely. There might be one of those that it's possible that if you just pick quickly, you could get one that you get one answer for, but there might be other x's or whatever that give you more than one answer. But this one, it was pretty easy. Okay with that? No problem. Okay, you guys ready to get going with the new stuff for today? Perfect. So we did last time, just to double check, we did sections 1.1 and 1.2. Is that correct? Yes. Okay. Thank you. This year I have 4 sections of honors for this class and 2 sections of regular, so I'm really doing the same thing every class for every, and it's just like the honors class is a little bit different than this class. I just want to make sure that I'm starting from the right spot. You know what I mean, guys? It's the first time in my career I've basically been doing the same thing every day, all day, which is nice, but also kind of dull in a way, you know? Okay. So in section 1.3, we're going to talk about continuity. Specifically, we're going to talk about continuous functions and kind of what that means. So we would say, for example, something like the function represented by the graph of a parabola is continuous because I can draw that parabola without having to pick up my pencil at any point. It's just one continuous, unbroken curve. In our Algebra 2 class last year, we talked about rational functions. And if you remember, the graph of a simple rational function has like a vertical asymptote and a horizontal asymptote. And if you draw the curve for that, you're going to have like one part over here and one part over here, right? That sometimes they look like this. That's not continuous because I can't draw that blue part of the graph without having to pick up my pencil. Does that make sense? So anytime you have like a break in your graph, that function would no longer be continuous. And we call those breaks discontinuities. And there's really 3 types of discontinuities. And I'm being a little vague about, like, notice I didn't write down any definitions for continuity or discontinuity. I'm intentionally not doing that because the actual technical definition is something that's well beyond the scope of this class. But all we really need to do is recognize something from a graph. Like the informal descriptions that I've given you are perfectly sufficient. But like, if you take a calculus course, you'll get the real definition of continuity that involves techniques that are well beyond the scope of what we're doing here, which is why we're not giving a formal definition for this new term. I just wanted to state that here briefly. So 3 types of discontinuity. One type, or the first kind we'll talk about, is called a removable discontinuity. So a removable discontinuity might have something that looks like this. So that open circle on my parabola is just like one point that's missing from the parabola. So that open circle means that there's a point not included on it. So it's just like I have a parabola, but there's like one little hole in it. So I'd have to pick up my pencil. So my removable discontinuity is this little hole in the graph. And you could also have a removable discontinuity where you have a hole where the point should be, but like the point is just moved somewhere else. Like it's not missing, it's just like in the wrong spot, kind of. That still counts as a removable discontinuity. I would point out to you guys, though, that in this sort of situation, the hole and the point need to be on the same vertical line. Because if they weren't, this would cease to be a function because it would fail a vertical line test. Does that make sense? Okay. And last year, if you remember when we talked about rational functions, you might have had something like you might have, we graphed or talked about stuff like this, right? And remember, in this sort of situation, we could reduce the x plus 3's. So we'd say the answer is like x minus 2 times x plus 2. But we'd have to include that x cannot be negative 3. If we're truly saying these two things are equal, because here, if I took the original problem, if I plug negative 3 in for x, I get 0 over 0, which is undefined. And if I look at just this part of the function, if I plug negative 3 in for x, I don't get 0 over 0, right? I'd get 5 or whatever. That's why we have to have the stipulation that x cannot equal negative 3, is so that we maintain equality between the beginning and the simplified. But when you have a situation like that where you have a rational function and you completely reduce something from the denominator, it's going to create one of these removable discontinuities. In fact, this function here is that graph approximates that example function there. So like if we look at the graph of this, let's fire that up real quick. So this is just a graphing software that I'm going to use for this example. I'm using this instead of the calculator because the picture will be a little bit easier to see for you guys. So I typed in my function there, x plus 2 times x minus 2 times x plus 3 divided by x plus 3. You'll notice here at negative 3, so let's change the background here. You can see here the little hole in the graph. See the open circle up there? So again, you're seeing that removable discontinuity. There's just like one spot in our graph that's missing. One little point. Is that okay? The next type of discontinuity we'll talk about is infinite discontinuity. So if you remember last year, again, when we graphed simple rational functions, all simple rational functions had a vertical asymptote on them. That vertical asymptote is our infinite discontinuity. We call it an infinite discontinuity because at that location, the graph is heading off towards infinity, either positive or negative infinity. Does that feel okay to you guys? Now, just for the record, like if both arrows are pointing up or both arrows are pointing down, still an infinite discontinuity, pointing opposite directions, whatever, doesn't matter. Also worth pointing out, Landon, do you have a question?
Like too?
Sure. Also worth pointing out, here in this case, this vertical asymptote is an infinite discontinuity. Not all vertical asymptotes have to be infinite discontinuities, but all infinite discontinuities are vertical asymptotes. And we've seen an example last year of a vertical asymptote that would not be an infinite discontinuity. Remember when we graphed logarithms? You had like a vertical asymptote, but then the graph of the log all looked like this. So there's an example of a vertical asymptote that is not a discontinuity because the blue part of my graph I can draw without picking up my pencil. So just to be clear, all infinite discontinuities are vertical asymptotes, but there are vertical asymptotes that are not infinite discontinuities. And that's why we're giving a separate name for this, because you can't just say a vertical asymptote because there's some that aren't. Is that okay? Okay. The last type of discontinuity we'll talk about are jump discontinuities. And this is one that we haven't ever seen before. So notice this jump discontinuity, there's like, I've taken part of the graph and like detached it from the other part and just moved it up or could have moved it down to a new location. Does that make sense to you guys, what you're seeing there? Now, one of the reasons we haven't really seen jump discontinuities before in our Algebra 2 class is that really the only way to create these is with something called a piecewise function. So in a piecewise function, we do one of these little curly brackets, and then we define our function with a different rule for different parts of its domain. So let's think here for a moment. So let's say that we have the piecewise function f of x equals x plus 4 for x is greater than 0. Actually, I'm going to switch that. I'm going to make this one less than 0 and this one greater than 0. Usually we set it up so the domains move from left to right rather than like right to left. And then we have for x is greater than or equal to 0, it's going to act like negative 5x minus 10. So if we think about what this is going to look like, for x is less than 0, it's going to act like x plus 4, which is just a straight line with slope 1 that has a y-intercept at 4. And then after 0, it's going to act like negative 5 minus 10. So again, that's going to be a straight line with y-intercept of 10 with a negative 5 slope. So it would look like, something like that. And there you can see the jump in between, right? Actually, I think if you had an excellent memory, when we defined absolute value functions, one of the definitions we gave for an absolute value function was a piecewise definition. That for x is greater than 0, I think, let me think. I think one of the definitions we give is like this. Like that's also a definition for the absolute value of x. Of course, yeah, no problem. So maybe we have seen a piecewise function like one time, super briefly, for like half a minute that we probably all promptly forgot, which is okay, not a big deal. So what I would say is a reasonable expectation for what I would expect you guys to be able to do with this is if I give you a function and its graph, can you identify what the discontinuity, what type of discontinuities are present and where? And again, all I'm giving is like a little sketch here. So if I look at the picture, what type of discontinuity do you see? Is it removable, infinite, or jump? Landon? Infinite? And how many do you see?
I guess
2. Now we've identified the number and the type. The last thing I would want is for you also to be able to give me the location. So remember that these are, the infinite discontinuities are asymptotes. For a rational function, the asymptotes occur when the reduced denominator is equal to 0. So to get the locations, all I need is to say this equals 0. I could solve that by factoring. Since it's a difference of 2 squares, that factors pretty easily. So I have 2 infinite discontinuities. One of them is at positive x equals 2, and the other is at x equals negative 2. Does that feel okay? Lily?
So, I have 2 questions.
Sure.
So the bottom, like the bottom of the graph, why isn't that in infinitive? Why isn't that like the third one?
So the discontinuities are the breaks in the graph, not the continuous parts of the graph. There's 3 continuous pieces, but there's 2 discontinuities because there's a break here and there's a break there.
Okay. And then why do you solve with the bottom part again?
So I remember that the infinite discontinuities are always vertical asymptotes.
Okay.
And for a rational function, the vertical asymptotes occur when the denominator is equal to 0.
Oh.
No problem. Again, like any kind of clarification question you need to ask, just shout it out, stop me if I'm going too fast or whatever. Like, it's important that you understand if you're like, I didn't quite catch that, or I didn't get it, or whatever. Like, say something. Emilio?
it's not that important, but you're not saying.
Right. Yes. When I'm recording at the same time, I tend to turn the sync off. I'll sync at the end of the lesson because it's just a lot of stuff going on in my computer and it lags sometimes. But yes. Yeah. No, I'm aware. Thank you. Let's look at another, okay? The other reason I turned the sync off, Emilio, is because you guys are also doing stuff potentially in your notebooks, and then it's trying to sync all that stuff also, which just like really ties up a lot of, the computing power on that's going on. So I typically during the day I'll turn the sync off and then just force the sync at the end to dump everything in. Okay, so if we look at this one, what type of discontinuity do we see? Removable. And how many? Good. So now let's find that removable discontinuity. So I know that that removable discontinuity is going to be generated by reducing this rational expression. So to reduce this rational expression, I'm going to start by factoring. So the denominator, there's nothing to do there, right? X plus 3 doesn't factor anymore. But the numerator is quadratic, and that should be something I can factor. It's the easiest possible type of quadratic factoring because the leading coefficient is 1, which is nice. So I'm just going to look for two things that multiply to give me -6, the last term, and add to give me, in this case, +1, because that's the coefficient on the middle term. So those things would be +3 and -2. So this will factor to x plus 3 and x minus 2. If I reduce, I can reduce the x plus 3's. So I know then that that set equal to 0 is going to give me my removable discontinuity. Is that okay with you guys? John?
So when we look at that, can we say x is equal to -3 because this is...
Right, that is the location of the discontinuity,
Okay.
right? So what that tells me, though, is that g of -3 is undefined. Because that's a discontinuity, because it is a discontinuity. There is no value for the function at 3, because that is the location of the discontinuity.
Would it also be okay to say x cannot equal -3?
So if you're talking about the location of a discontinuity, I would prefer it you'd write as x equals.
Okay.
If you reduced this, you would say that like this is equal to x minus 2, where x is not equal to -3. Because that's, again, where the discontinuity is, so you can't have a value there. So that's where you would use not equal to -3, is where you're like specifying the function can have no value there. Or if you're saying, okay, this is the location of the discontinuity, then it's an equals.
Okay.
Does that make sense as the difference of how to use those two? You're welcome. Again, that's a nice question because it's easy to get kind of confused, especially because we do stuff with not equals and equals all the time, interchangeably with the discontinuities. It's just a question of like making sure we understand like what question am I really answering as to when I would use one versus the other. And our last example here, x cubed minus 2x squared plus 3. And my graph for this looks about like that. What discontinuities do we see here? Anybody? It's kind of a trick question. There aren't any, right? This is continuous. Should write that red. As a little tip going forward, this is a polynomial, right? Everybody can recognize that just by the form that it's written. All polynomials are always continuous. So that's one where you don't even need the graph really if you know that fact, which is nice, right? Like whenever you have an all statement in mathematics, it's like, ooh, that's pretty good. If it's always this thing. All right. That'll close section 3. In section 4, we're going to talk about increasing and decreasing. So increasing and decreasing are, again, topics that we would have talked about last year in our algebra course. And they're really just descriptors that have to do with the behavior of our functions. So they're kind of like adjectives, right? They're describing some property of a function. So basically the way that I like to talk about it is you have like 3 different, when we talk about increasing and decreasing, we have like 3 different possibilities. So you have, let's say we have a graph that looks like this. The way I like to think about it is that I have like a little man or woman or whatever that's walking along the graph from left to right. So if we're walking uphill, that is increasing. If they're walking along a flat part, that's constant. And if they're walking downhill, that's decreasing. So again, I'm going to skip giving like a super formal definition for this because I think that this is really intuitive if you think about it this way, and it's going to be, I think, really effective. And I'm not going to bog you down with like, the fact that an increasing function says on a given interval, for any 2 points on the interval, a positive change in x results in a positive change for f of x. Like, ugh. Think about your little man walking along the function. If he's going uphill, it's increasing. If he's going downhill, it's decreasing. If he's flat, it's constant. That's I think, more practical for what we're going to be asking you to do, right? Because I'm not going to ask you to prove that that like the graph is increasing along, this interval. I'm just going to ask you to find the intervals where it's increasing or decreasing. So like just being able to look at the picture is really all we want to be able to do. Does that make sense for you guys? Okay, so I'm just gonna make up some points here. So let's say that this is 1, 2, and let's say this is, can't be 1, 2, you goofus. Try -1, 2. And let's say this one is 3, 2. If I was talking about my intervals that are increasing, I'm talking about this part of the graph, right? When we describe intervals on a graph, we're always talking about its x coordinates. So if I look at this part of the graph, starting at the left, the x-coordinate for an arrow pointing to the left is like negative infinity. So you guys okay with that? And it stops increasing at this point, whose x-coordinate is -1. And for intervals of increasing and decreasing, we always are going to use parentheses. So there's no worries there. There'll always be parentheses. They won't ever be intervals. Next, our graph turns to constant. It starts becoming constant here at -1. And it stops becoming constant because we start moving downhill at 3. Again, all we care about are the x-coordinates. Does everybody kind of remember doing this last year? I know that I do this in my class and we spend quite a bit of time here, but did Miss Morgan teach the other algebra class? Is that right? Yeah. Did she do this? Do you remember? You might not remember. You're not sure. You don't think so? Okay. Well, we're going through it slowly. I think that it's still okay, right? I'm not going too fast through this. Okay. The next section would be decreasing. So here, the decreasing starts at this point, whose x-coordinate is 3. And it continues decreasing forever since we have the right arrow. That right arrow is going to tell us that would be going all the way to positive infinity. Does that feel okay with you guys? Okay. Let's do another example that's a little bit more complicated here. I'm going to, because it's a little bit more complicated, I'm going to generate the graph for it with the computer so that we have a nice visual of what's going on. So I'll just import that in here so we have something nice to look at. And go ahead and assume that, like, wherever the graph is leaving this, like the viewing window there, there's an arrow at the end of those parts, right? Hopefully that's, nobody finds that a stretch, like there's an arrow at all of those places, right? That's cool. Not a big stretch for you guys, I hope. Okay. So let's look for some sections that are increasing. How many increasing sections do you guys see to this graph? I see just 2. Right? If I start here and I walk along the graph, I'm going uphill all the way until I hit that asymptote. So that whole section is increasing. You guys buy that? If I move to the next section, if I start down here, I walk along the graph, I'm going uphill all the way till I get to 0. And then it changes, right? Because now I'm start walking downhill. And if I move to the next spot, I start up here and I'm going downhill all the way. So I see 2 increasing sections and 2 decreasing sections. Do you guys buy that when you look at the graph? Again, the key here is remembering to look from left to right. Is that okay? All right. So let's look at each one of these intervals. So again, remember that when we write these intervals, we're talking about x coordinates. This first interval, we started at the left-hand arrow, which is -infinity. And we go all the way to here, which is at, if I look down on my graph, looks like -3 is where that arrow stops at. Everybody agree with that? Oops, I don't know why I put a parenthesis there. And then because I have a second section, I'm going to put that union symbol. Remember that from when we did domains just a few minutes ago? Okay. So we'll start here. Again, the location there was -3. And we ended here at 0. Again, remember, we're always talking about x coordinates and not y coordinates. Okay. Next up are our decreasing sections. Our first decreasing section begins here, whose x-coordinate is 0. And it continues decreasing all the way to here, where the x-coordinate is, looks like 3 to me. And then we'll need the union symbol because we move to the next part that starts here, still at 3, and ends here at the right arrow, which is positive infinity. Is that okay with you guys? Cool. All right, one more topic to talk about in this section, and then we're going to be finished for today. That last topic is extrema. So there's 2 types of extrema. There is maxima, which is the plural for maximum. And there's minima. That's the plural for minimum. Oops, minima. So a maximum is like the highest points on a function. Actually, I'm going to take off the superlative. We're just going to say high points on a function. And minima will just be low points. And there are two types of maxima, and there are two types of minima. So you have the absolute, or sometimes we'll call it global. You could use those two terms interchangeably. They mean the same thing in this context. Maximum, which is the highest point or points. And then you have local, which is the highest point in a neighborhood. So just like not looking at the entire graph, but just looking at like some smaller section of the graph, like is this a high point in that neighborhood, right? Like you might be the smartest person in your class, but you might not be the smartest person in the whole school, right? You're locally the maximum, but you're not maybe the global maximum. Does that kind of make sense as to what we're saying? And we'll draw some pictures here to really clarify this and then talk about how to use our calculator to do these sorts of things. And then for minima, it's the same thing. You have global or absolute. Which is just like the lowest point or points. And then the local, same idea, it's the lowest point in that neighborhood. Sorry for my penmanship. If you can't read anything, holler at me. I'm trying hard not to write terribly, but it's just like I write small and I write fast, and the combination can sometimes get a little illegible. If you can't read anything or you need clarification, please don't hesitate to ask. I will not be offended at all, because there's times when I look at stuff that I read and I'm like, what the heck did I write there? I know it's not the worst penmanship in the world, but it's not great either. It's like C- penmanship. I get it. It was this and spelling were the two things I struggled with as an elementary school student. So if you see things spelt wrong, that's the other. That's on me also. It's probably wrong. Okay. So if we take a look back at this graph, for example, real quick. This graph has one extrema here. That extrema is a local maximum, because there are lots of points on the graph that are higher than that one. But if you look at just one little section, it is a high point in that section. We say there's no global maximum because you have an arrow going up forever. So any point you find, there's going to be another one higher than that. And it has no global minimum because we have an arrow going down. And any point you pick, you can always find one smaller than it. Everybody okay with that? Okay. So let's do an example, and we'll use our calculator to find these maxima or minima. So if you have your calculator with you and you'd like to follow along, I would invite you to do so. If you don't have your calculator with you, my recommendation would be then to go back with the video to this part and kind of follow along on your calculator when you get it, just so you've practiced doing this before you try to do on your own in the homework, which, again, some of us are really good with the calculator. Some of us need to do it a couple of times to really remember. You know what I mean? All right. So what I'm going to do to find maximums and minimums on our calculator, we need the graph of the function first. So if you remember from last year, to graph a function, you start by pressing the y equals button that's in the upper left-hand corner. And now my calculator has some stuff in it already. I'm going to clear that out. I would invite you guys to do the same. And I'm going to scroll all the way to the bottom because my calculator's been sitting in my backpack for a while, and sometimes if like the cover's off, I end up with googly-gok down at the bottom. I'm just going to scroll all the way to the bottom and make sure they don't have anything in any of the function slots. Next thing I'm going to do is I'm going to check to make sure up here at the top where it says plot 1, plot 2, plot 3, I want to make sure that none of those are highlighted. So for example, it shouldn't look like this. If it does look like that bell is a lie. I'm going to move my cursor up to that spot and just press enter to unhighlight it. And now I'm just going to type in my function here exactly as it looks onto my calculator. So the X button is right here next to the alpha. And then the caret button here above the division sign will give you an exponent. And then everything else is just like the same stuff over and over again. So I'm just going to type in the rest of my function exactly as it looks on my sheet of paper. Now, to graph this, since it's been a while since I've used my calculator, I don't remember what my window was set at last time, and it could be something crazy where I don't get a good picture at all. What I'm going to do is I'm going to press zoom, and I'm going to select Z standard. So the zoom is right there along the top row in the middle. And the command I'm going to pick is Z standard. That's just going to give me the normal viewing window from -10 to +10 on both the X and Y axis, which is probably going to be good enough for what we're doing here. How do we do on getting a picture? Did we get the right thing? I'll take it your silence as yes, you did. So if I look at my picture here, I see a global minimum right there, where my mouse pointer is. I see a local maximum here, where my mouse pointer is. And I see a local minimum here, where my mouse pointer is. But I have no global maximum because I have like arrows pointing up at the end of my graph. So I'm just going to go ahead and record some of that information. So I have a global min. I have a local min. Oh, I'm sorry, let's write them in the order that we see them. Local max, and then a local min. And I'll write global max none here, just so I don't, as long as we've identified that, let's write it down. So far, so good. What I'm going to do now is use the calculator to find the actual coordinates of these points. So to access the menu where I can get the commands to find maximums and minimums, I'm going to press the second button, which is the blue one, and then the trace button on the upper row. And if I look at this menu, which command do you think I want if I'm looking for a minimum? It's not a trick question. I want the minimum command. So let's find that global minimum first. So I'm going to scroll down and pick the minimum command. Now you'll notice on my calculator there's a question here. It says left bound. So what the calculator is asking me to do is to move my cursor, which you can see here on your calculator, somewhere left of where that minimum is. So I need to move it like somewhere over here. So I'm just going to use the left arrow to move my cursor till it's somewhere over here. Doesn't really matter where it is, it just has to be on the left side of that minimum. And then I'll press enter. Now the question has changed. It's asking me for a right bound. So I'll do the same thing. I'm going to move it somewhere over here so that it's on the right side of that minimum. I'll just press the right arrows until I see it in the spot that I want it. That looks good. So I'll press enter again. It says guess. The guess doesn't matter if we picked a narrow range like that. So I'm just going to press enter again right where it's at rather than wasting my time. And there's my minimum at the bottom of the screen. So on my paper, I'm just going to copy that down. And I think I'll give 3 decimal places. Negative 2.243, comma, negative 9.653. So it gave me an X and a Y, so I'm just going to record the X and the Y there. And I'll go 3 decimal places, seems appropriate. I don't want to write them all down. That's a little bonkers. But I could if I wanted to. Who wants to write that much? She golly willikers. Feels so far so good? Let's find that local maximum next. So to do that, I'll go back to that menu. So I'll press second and the trace button again. But this time I'm going to choose the maximum command. It's going to ask me the same 3 questions, left bound, right bound, and guess. So I'm going to start by moving my cursor somewhere here, which is on the left side of my maximum. So that looks good. And now press enter. Now for my right bound, I'm going to move my cursor somewhere over here. So I'll press it a couple of times. That looks good. I'll press enter. And then press enter again for my guess. And notice my cursor is at that minimum or that maximum. So I'll just record that values for the X and the Y. Again, I'm just going to round to 3 decimal places. And then I'm going to repeat that process one more time for the other local minimum. And then I'm going to be done. Does that sound okay with you guys? So second and trace again. This time choosing the minimum command because we're doing a local minimum. Again, I'm going to move. It's asking the same 3 questions, left bound, right bound, guess. So I'm going to move my cursor somewhere over here and press enter. That looks good. Now for the right bound, I'm going to move it somewhere over here and press enter. That looks good, and the guess, wherever it's at, is fine. And again, I'm going to record 3 decimal places. Now, if I wanted to, I can use that information to record my intervals of increasing and decreasing. So if I'm going to a minimum, that's the first thing I encounter, right? Is that global minimum? If I'm going towards a minimum, I must be decreasing down to that minimum, correct? If we're starting to go to a minimum, so I know I'm going to be going from negative infinity to that minimum. And then if I go from minimum to maximum, I'm going to be increasing there. And then I go from maximum back to minimum, That'll be decreasing now. And then if I have the other side of a minimum, the minimum looks like this. So the other side of the minimum must be increasing. And if that's the last thing, it must then be increasing forever. So you notice that the bounds of my intervals are always the x-coordinates from my extrema, right? The extrema have to be the boundaries of my changes in increasing and decreasing functions. Or, I'm sorry, let me rephrase. The extrema have to be the boundaries for my changes of increasing and decreasing for continuous functions. If I have a discontinuity, you could also change increasing and decreasing at a discontinuity. It doesn't also have to be an extrema. All right. That wraps up what I wanted to do today. We're going to add on a couple of problems to your homework that are only concerned with this increasing and decreasing section. So we're going to add on 13 to 18. We meet again Friday, so this would be part of the Sunday homework check. What we do on Friday would put part of next week's homework check, so you'll have a chance to see me in class and ask questions about it before that part is expected to be turned in. But this will be updated, so I'm going to just, in my Notre Dame or whatever, the name of the homework assignment, I'm just going to add, to include these numbers also. So I'm not going to make a separate homework assignment. I'm just going to change the label a little bit to include these numbers also. Is there anything else I can do for you to help remind you of what to do on Sunday? Would it help to have an announcement on the My Notre Dame page? Or do you just need the assignment to show up well labeled? And that should be good. I don't know what your end looks like, and I'm just trying to, when I make them in Power School, it has, it automatically puts the assignments onto the calendar that you can see, right when you log in. And I don't think this is doing that, but I just wanted to, I don't know how you're using it, and I don't know if there's anything else I can do additional communication-wise to make it easy for you to remember what's due. But if you think of anything, or you're like, oh, this is the way if something is here, that would help. If you tell me, I can see if I can make sure I do that. For right now, I'm just going to change the assignment. If it turns out that doing something else is really helpful, let me know and we can start adding that on, okay? Again, it's a new communication system, so I'm getting used to it as you guys are. Okay? Cool. We just got a couple of minutes left, so you guys can relax here until 9:05 when we have to hit the road. Thanks again. Again, I appreciate the effort and the attention and the, staying focused through the lesson and participating and asking questions. That's all very good. Again, mathematics is one of these things if you stay on top of things and you try every day, usually good things happen and nothing usually doesn't get too overwhelmingly difficult. If you try to sprint walk it, oftentimes that's recipe for trouble. But if you just kind of plod away at the same pace the whole time and stay on top of things, usually that makes things more manageable. So I would encourage you to kind of stay on top of things. Some subjects, it's easy to sprint walk. Mathematics is not one that you want to probably do that with. I mean, some of us are smart enough that we can get away with it, but most of us are would do much better just plotting. You know what I mean? Okay. Thanks, everybody.